Okay, so we're going to try Giancoli 6.1. We're going to talk about work. Work done by constant force. The work done by constant force is defined as the distance moved multiplied by the component of the force in the direction of the displacement. Work is equal to force times distance times cosine theta. So what this means, this object is moving in this direction. We're applying a force at this angle, okay? But the only force that we can count for work has to be just a horizontal component because it's going in the same direction as the displacement. So we have to find what the horizontal components of the force, which is the force times the cosine of theta. So force cosine of theta times the distance. That is how we find work. Now, if we were just pushing it in this direction, right, and if it was all our force was being pushed in the horizontal, it would just be force times distance times the cosine of 0, which is 1. So it would just be force times distance. All right, work done by a constant force. Units of work are joules. 1 joule is 1 Newton times meters. And as long as this person does not lift or lower the bag of groceries, he is doing no work on it because the force is being upward while we're carrying the groceries this direction. So the force he exerts has no components in the direction of motion, which means if it's perpendicular, there is no work being done. Okay? If it's perpendicular, there's no work being done. So if we want to do or solve a problem about work, 1, free body diagram. 2, find a coordinate system, again, up and right or positive, down and left or negative. If we want to apply Newton's laws to determine any unknown forces, if need be, we want to find the work done by a specific force. Again, force times displacement, as long as it's going in the same direction. And to find the net work, find the net force, and then find the work it does, or find the work done by each force and add them together. Either way, it'll work, and we'll show you that in a second. What if we have work done by forces that oppose the direction of motion, such as friction, will be negative. So when we talk about friction work, that's negative. And then centripetal forces do no work, as they are always perpendicular to the direction of motion. So we got centripetal force going in, motion going this way. They've got a 90-degree angle. They're perpendicular. Therefore, there is no work being done on the Earth, on the moon by the Earth. Work done in a crate. Person pulls a 50-kilogram crate 40 newtons along a horizontal floor by a constant force of 100 newtons, which acts at a 37-degree angle. The floor is rough and exerts a frictional force of 50 newtons. We want to determine the work done by each force acting on the crate and the net work done on the crate. Do it now. Okay, so here we got the drawing. We got gravity, normal force, force applied, and frictional force. Now, and I put in red, and again, went 40 meters this direction. So when we're talking about being on the same plane, right, friction's definitely on the same plane as this, and then also the different color, the x component, right, the horizontal component of our applied force. So let's put some numbers in here. We know it's a 50-kilogram crate, so our force of gravity is 50 times 9.8. Our normal force will be the same as the force of gravity because we're on a flat surface. So those forces are going to balance. Our applied force here is 100 newtons, and then our frictional force is 50 newtons. So we want to find the work done. Now, gravity and normal force aren't doing any work because we're moving in this direction. So the work on these is going to be 0. So these really aren't going to be important to us in terms of work. What's going to be important to us is friction and the horizontal component of our applied force. So let's look at the force of friction first. Our force is negative 50, and the distance is 40. Why I say negative 50? Because it's going this way. So our frictional force is going to be 50 times 40. Don't know why I went to that extent, but it's negative 2,000 joules. So 2 kilojoules going to the left. Now let's see for our applied force of 100 times our distance 40 times the cosine of our angle, which in this case we found that angle to be 37 degrees. So this is 37 degrees. So 100 times 40 times the cosine of 37, 3,195 joules. Okay, so this is the two forces that are doing work. Again, these two aren't because they're perpendicular to our motion. So now part B says the net work done on the crate. I just add these two together. So I take negative 2,000 plus 3,195, and I get net work of 1,195 joules. Work done on a backpack. We want to determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of height 10 meters, as shown in the diagram. We also want to determine B, the work done by gravity on the backpack, and then C, the net work done on the backpack. So we're going to assume the motion is smooth and at a constant velocity. So there's going to be no acceleration to find this net work. Okay, so we got our backpacker here, and that's not very good. It's here, and our backpacker is going to go up to here. Okay, and we want to find A says we want to determine the work the hiker must do. Okay, so let's talk about the backpack here. So our backpack is here, and we got our applied force or our lifting force, and then we got the force of gravity here on our backpack. It says we're going at a constant velocity, so our force applied to lift it minus the weight is going to equal MA. MA is 0. So force applied minus force of gravity will equal 0. And force applied is going to be equal to the force of gravity, which is mass, which the mass of our backpack is 15 kilograms, and then we multiply it by 9.8. So 15 times 9.8 is 147 newtons. So that's the weight, and that's also the applied force to lift it. Okay, it's 147 newtons. So we've discovered that. Now we want to find the work done by a specific force. So let's talk about the work for our applied force, all right? The force that we apply is going to be 147 newtons. And now we're walking it up this thing, and we're thinking, gosh, I got to worry about angles and all that, but let's think about the work done. We're starting at the bottom, and we're going to the top. So the distance traveled is going to be 10 meters, right? So I got 147 times 10, and that equals 1,470 joules of work, right? And we're gonna, and since we're lifting, we're going this direction, and we're going in this direction. Everything's on the same plane. We don't have to worry about the angle. 1,470 joules. So it's kind of a shortcut way. We don't have to do any math. We don't have to worry about inclined planes, because I'm sure that's what you all were thinking when you saw the problem. So now we got the work for that. So now we want to think about the work that's done by gravity, right? And we think about that work. It's going to be force times distance. So the force of gravity is 147 newtons, and that's going straight down. And we're going up 10, so this one's going to be negative 10 meters is going to be our distance traveled. It's going to be negative 1,470 joules. So that's our work. That's our work due to gravity. And then the last part is net work done. We add these two together, and net work is going to be 0 joules. Okay. So even though the net work is 0 joules, the work that the hiker does to the backpack, right, to get it up to there is still 1,470 joules. So when this backpack gets up there, that backpack has this much energy. All right, it's just counteracted with gravity, but we still have that much energy given to our backpack, even though we're fighting against gravity. So don't let this net work stick in. Go, oh my gosh, it has no energy. It does have energy. It has energy from the height that we give it, and that is 1,470 joules. The big takeout from this is that even though we have this slope and we don't know the angle, and we think about the math we have to do, if we take something and walk it up a ramp to here, all we're doing is raising the height. And when we raise the height, that's the distance. traveled. How long this ramp is, it could be a steep ramp, it could be a shallow ramp, doesn't matter. We're given energy based on height. And when we talk about potential energy, it'll make more sense. But just understand that we're worried about from point 0 to point 10 here, not this distance, when we talk about giving it height. And since we have these two forces on the same plane, it makes it really easy for us. And then lastly, does the Earth do work on the moon? We kind of answered this already. The moon revolves around the Earth in a nearly circular orbit, kept there by gravity. Does gravity do positive, negative, or no work? Well, we've already determined that since the motion of the moon is going this way and gravity's going inward, it's perpendicular. Therefore, the answer is C, no work.